Okay, our next speaker is Nicole Gillett from Riverlane.
Hi everyone, I'm Nicole Gillett from Riverlane. I'm a software engineer at Riverlane, which is a quantum computing company based in Cambridge in the UK. And today I'm going to be talking about parallel and low latency streaming decoding of quantum error correction codes, which can really be summarized as a scalable solution for quantum error correction, and something that we like to call independent windowing. So I think any discussion about windowing really needs to start with why we need real-time decoding, which we've definitely alluded to a few times in this session. But just to reiterate, certain circuits contain branching logic that can depend on the outcome of a previous measurement, which must therefore be decoded in order to be reliable. As you can see here, we have an example gate teleportation circuit, and whether or not to apply the S gate is dependent on the Z measurement outcome. So one of the first ways that people tried to enable real-time decoding was something called sliding window, where effectively the decoding graph is broken up into these windows that consist of a commit region and a buffer region. And the buffer region is just a way of us saying that we're less confident about defects that are occurring further ahead in time. However, Terhal identified a fundamental limitation of this system, which is that if the decoder isn't fast enough to keep up with the rate of syndrome generation, we'll encounter the backlog problem and will effectively experience an exponential slowdown during the computation. So people started looking into various ways to try and parallelize the system. For example, it was realized that actually windows can be decoded in any order. So for example, you could decode the commit windows in one pass, and then you could decode all of the buffer regions between them in a second pass. We also have the Fusion Blossom algorithm that splits a decoding problem into two and then fuses their solutions together in a recursive step. So when we were thinking about what sort of real-time or parallelization we wanted to do for LCD, for example, we were thinking about all these different methods, and we noticed this common theme, which is that they all seem to have the transfer of data between windows in the form of artificial defects. And not only does this contribute to the overall latency of the system, but it also can impose a constraint on the types of windows that can be constructed. So we were really curious to understand if there was a way to effectively break up the decoding problem into individual decoding windows that could be treated as independent decoded windows and solved completely independently. And what we found is that it's actually possible to do this with only transferring one bit of information from each window. And we also have been able to do this whilst making the minimal amount of changes possible to the decoder. And at Riverlane, this is something that we're really interested in because we work with lots of different types of decoders. So for us, we really wanted a windowing scheme that we could potentially use with lots of different decoders. You know, we didn't want the real-time decoding element to be dependent on the structure of the decoder in any way. So the fact that we were able to do it without making a significant amount of changes was really appealing. So if you want to define a window as a sort of independent decoding problem, it's necessary to define the commit region in the center of the window and have two buffer regions on either side of that commit region. And what this does is it effectively means that the window has sufficient information to be treated as an isolated decoding problem and solved completely independently. So that was our first insight. The other thing that we wanted to do was to see if, instead of defining the commit region, for example, by introducing some status for every node, saying whether or not it was in the commit region and making lots of changes to the decoder and then having to make those changes when we make another decoder, we were like, how else could we define it? And so we thought, well, the definition of the logical is something that every decoder has. So why have the logical kind of, defined throughout the whole window when we're only interested in the logical that's defined in the commit region? So what we did is we actually chose to define the commit region through the definition of the logical. So you can see here in the image here that we basically define the commit region of our window through the definition of the logical. And in the growing stage of the algorithm, If any of the edges cross over the logical section, we say that they have flipped the logical state of the system. And then when we're looking at all of the outputs of all of these windows, we can basically just aggregate all of the outputs from the window to say whether or not the outcome of that window has flipped the state of the logical, and that will basically give us the overall logical correction on the system. So effectively, whether or not the logical state has been flipped is all encoded in one bit of information. So when we first modeled this approach in software, we actually noticed that there was a discrepancy in this independent window decoder and a comparative fixed window decoder. And what we realized is that actually the decoder could make different decisions between decoding windows. And as we went up to higher code different distances, these differences became particularly prominent around the boundary of the logical. So we wanted to see if there was a way that we could resolve this and force consistency between windows without making any specific changes to the decoder. And once again, we were able to use the definition of the logicals in order to enforce consistency between windows. So what we did is we introduced this concept of the fake logical. So you can see in this diagram here, we have two fake logicals that exist around the logical of interest or the committing logical. And whenever the decoder has to make a decision about which logical to choose, it always chooses the logical with the lowest cluster index. And this effectively forces the decoder to make the same decisions between windows, and it forces consistency between windows. And really interestingly, this is something that LCD, Riverlane's local clustering decoder, does out of the box, because LCD automatically chooses the logical with the lowest cluster index. So once we were happy with the accuracy of this potential solution, we decided that it was time to take this down to FPGA. So at Riverlane, we care a lot about trying to build a system for quantum error correction that has very low latency. That's why we like to take the decoding technology down into FPGA. And when we implemented this for LCD, we found that we were comfortably under the 1 microsecond per round decoding time, which is required for superconducting qubits. And we were, and we were able to demonstrate support for up to distance 11. So what you can see here is, an example FPGA chip, and we're saying this is a solution for error correction all the way up to distance 11. So even though our decoder is actually fast enough to keep up with the rate of syndrome generation, the way that independent windowing works in terms of treating every window as a completely isolated decoding problem puts a constraint on the overall latency of the system, because as soon as a region's worth of syndrome data is generated, we can kick off an instance of a decoder in order to begin decoding. So we don't have to wait for any other part of the process before we can start decoding that window. So overall, what we've shown is that it's actually been possible to turn LCD into a streaming decoder without actually making any changes to LCD itself, but simply from the way in which we define the configuration of the windows. And yeah, we're really excited to say that, this is something that can be accessible for people who want to perform quantum error corrections for their system through the Delta Play system that we're developing at Riverlane. So yeah, just say thanks to everyone who's been involved in this idea at Riverlane, and yeah, definitely come and visit us at booth number 174. Thank you.
We have time for a question or two.
Oh, sorry.
Yeah, thank you for the nice talk. I don't know if I missed this, but I'm assuming that most of what you guys looked at so far relates to the service code. And I was wanting to ask whether you guys are also looking into novel types of codes and their decoding. Do these techniques of independent windowing also apply to, let's say, LDPC codes?
Yeah, well, that was kind of like one of the appeals of this technique, is that we wanted it to not be dependent on the code, because one common design pattern with FPGAs is that you might move information down windows, like down into a different window, and make use of pre-existing node connections within the FPGA. And that's fine if you're dealing with like a rotated planar surface code. But if you start going to like hypergraphs, for example, then that breaks apart. But because every window can be treated completely independently, there's no dependence on the structure of the underlying decoder, then there is definitely the potential for it to be expanded to other types of codes.
Cool, thank you.
Nice talk. So I was curious. So if you define the window of the decoder based on the logicals, would introducing the fake logicals take away that advantage, or is it fine?
Well, I think the thing that really appealed to us is like the definition of the logicals is something that every decoder has. So whether that's one logical or two or three logicals, it's something that would be there already. So it was kind of, there wasn't any additional effort required, if that makes sense.
Okay, yeah, I think so.
Okay, let's thank the speaker again.